Welcome everyone. We just heard an excellent ITC colloquium by Duffell, and he will speak in a few minutes about something else or related. I should say that next week we have a change in the location, and that's because of the Einstein Symposium. There will be plenty of Einstein Fellows here using Phillips Auditorium, and so we will need to move the lunch to Pratt. It will be at the same time, 12:30 to 1:30. But as you well know, that room is much smaller than this one, so it will be first come, first serve. We will try to accommodate as many sandwiches as we have usually, so that in the worst case, if you come too late, you can eat it in your office. We cannot provide the streamed web broadcasting in that room. We can do it here, but this room is used. Another change next week because of this is that the ITC colloquium will have to take place at 3 p.m., 3 to 4 instead of 11 to 12. And it will also be in Pratt. So keep in mind, next week it's all in Pratt, lunch and the colloquium. At a different time for the colloquium, 3 p.m. And in 2 weeks, the ITC lunch will be longer than usual to compensate those that will not be able to make it next week. But the actual reason is that LIGO will have a press conference. And if you want to know about what, just read Nature magazine from 3 weeks ago. So there are very strong rumors, and they are not being denied. Okay, so for today's program, we'll start with Nia Imara, who as of this academic year is the John Harvard Fellow in the Physical Sciences at the Faculty of Arts and Sciences at Harvard. That's a new position that just opened this year, and previously it was Life Sciences primarily. And she will talk about searching for exoplanets in unusual places near X-ray binaries. And then we'll hear from Paul Duffell that will speak about, he's now at Berkeley, and he will talk about 1D modeling of Rayleigh-Taylor instability in supernovae. And then we'll hear from Graur, who is here at the CFA. He will talk about the compact forms of tidal disruption events. And finally, we'll hear from our colloquium speaker today, Dava Sobel, who is sitting over there, just behind a few people. And she's an author and wrote a wonderful book that I recommend all of you to read. The Glass Universe, about the women astronomers here that worked in this particular room, like over a century ago, or was it one of the nearby rooms? Oh, it was building C. Okay, so Erwin is correcting me, it was building C nearby. And so she will speak at lunch about adventures in science writing. Nia.
Good afternoon, everyone. My name is Nia Imara. Now, I've given a couple of talks here at the ITC Luncheon related to the bread and butter of my research, star formation and cosmological dust. But today I'm going to talk about something very different. Today, I'm pretty excited to tell you about a fun project I've been working on in collaboration with Rosanne DeStefano. We propose using the transit technique to search for planets around X-ray binaries. In our paper, we consider the possibility that some X-ray binaries host planets, and we propose examining the X-ray transit light curves of such stars to discover the potential planets orbiting within or around them. Just to remind you, X-ray binaries are gravitationally interacting binaries in which a stellar remnant accretes matter from its companion. The term describes binaries where the accretor is a neutron star or a white dwarf or a black hole. And It turns out that planets in binaries may be common. As of today, roughly 70 examples are known of planets orbiting one member of a binary. These are called S-type or circumstellar orbits. About 20 cases in which the planet orbits both members are known among the roughly 1,000 eclipsing binaries observed with Kepler. These are called P-type or circumbinary orbits. The first known P-type system consists of a planet orbiting a pulsar and a white dwarf, and was detected from observed changes in the travel time of the radio pulses. This system passed through an epoch as an X-ray binary, during which the giant progenitor of today's white dwarf transferred mass to the neutron star, spinning it up. Planets have also been discovered in P-type orbits around binaries which will become CVs during their next evolutionary phase. These so-called pre-CVs contain a white dwarf, the remnant of a giant that filled its Roche lobe under circumstances inconsistent with dynamically stable mass transfer. The giant's envelope was transformed into a common envelope within which the white dwarf and its companion spiraled closer together but didn't merge. Eventually, the companion star will fill its Roche lobe too, and the binary will become a CV. If the planet is retained, it will be in orbit with an X-ray binary. Now, since planets have been found in P-type orbits both prior to and after the binary is an XRB, it's important to consider planets during the XRB phase. X-ray light curves, in which the donor star blocks out some of the X-ray emission, provide ideal opportunities to search for transits because the sizes of X-ray emitting regions can be so small that the passage of a planet could produce a sharply defined total eclipse. For example, in certain states, emission from a white dwarf emanates from an area comparable to its surface area. And that's the case with the binary system HT-CAS, which contains a white dwarf and a low-mass companion. In systems like this, an Earth-sized planet could cause a deep eclipse, and larger planets could produce total eclipses. Our main goals in this study were to examine the parameter space of stable orbits for planets in XRBs and to study the characteristics of expected light curves, all in order to give us an idea of the feasibility of detection. In their well-known paper, Holman and Weigert asked the question, what is the critical distance near a binary at which low-mass planets can persist for a long time? Inside this innermost critical separation, planet orbits are unstable, and at larger distances, orbits can last for a long time. Holman and Weigert addressed this question numerically, and they determined a functional form of the critical separation that depends on the binary separation, the eccentricity, and the mass ratio of the binary. So we use this formalism as our starting point, and in this way we make predictions about the orbital separation, periods, and transit light curves of the planets we might detect in XRBs. When mass transfer occurs because the donor fills its Roche lobe, the binary's orbital separation is set by the condition that the radius of the donor equals the size of the Roche lobe. Under that assumption, we get this plot of the binary separation as a function of binary mass ratio for a white dwarf having a fixed mass of 0.8 solar. And as the mass ratio increases, you can see that the separation increases from less than a solar radius to several solar radii. Overplotted are data points of binary separations for real CVs. And we do fairly well at reproducing the intermediary mass ratios. I'll note that mass transfer often occurs through winds, which can be driven by radiation from the accretor, for instance. In such case, the separation would be larger than it would be for Roche lobe filling systems. Using Holman and Weigert's formalism, this plot also shows the critical separation for single planets in S-type or circumstellar orbits and P-type circumbinary orbits. Keeping in mind that larger orbits than the critical values are possible for planets, it's interesting to note the pile-up phenomenon observed around main sequence stars. You might remember this plot from Caitlin Crater's talk last week, showing how the Kepler sample of circumbinary planets tend to have orbits right at the critical radius. If this pileup is real, and if planets and XRBs exhibit similar behavior, then it's possible that they too reside close to their innermost stable separation. We also consider tidal disruption. For S-type orbits, if the critical zone allowed by the stability calculations is too close to the star within the tidal disruption limit, then the planet would be ripped apart and wouldn't exist for us to detect. So as long as the critical semi-major axis is greater than the tidal disruption radius, the planet is safe, at least in this respect. This plot shows the critical semi-major axis again, now as a function of the donor star mass. The horizontal lines mark the tidal disruption radius, which just depends on the stellar mass and the planet density for Jupiter and Earth-like planets. So for instance, an Earth-like planet in a circumstellar orbit around a white dwarf would be ripped apart for binary separations less than about 1.3 solar radii. Since the mass of the donor would have to be pretty high in order to be large enough, in order to have large enough separations for the planet to survive, this means that for most realistic CV systems, S-type orbits are extremely unlikely. However, for craters having higher mass, we can find realistic, stable S-type orbits. In this example, with a 10 solar mass black hole, we see that stable orbits are allowed for Earths, where the secondary star is at least about 2 solar masses, and for Jupiter's, where the secondary mass is at least 4 solar masses. In the next part of our paper, we make some very simple models of the transit light curves. We focus on the circumbinary case. In this illustration, the star should be regarded more generally as the region of X-ray emission, which could be about the same size or smaller than the planet. In this first set of examples, we keep the mass of the donor star fixed at 1/10 of a solar mass and examine what happens when we increase the mass of the compact accretor. We consider both Earth and Jupiter-sized planets in solid and dashed lines, and as the white dwarf mass increases, the mass ratio decreases, and therefore the transit duration becomes increasingly short. Meanwhile, the transit depth, which depends on the ratio of the planet and X-ray source areas, for Earth-like planets, this transit depth gets deeper as the white dwarf mass increases, because the white dwarf gets smaller as its mass increases. Meanwhile, Jupiter-sized planets completely eclipse the white dwarf in each case. So assuming that the size of the X-ray emitting region in the CV is comparable to the size of the white dwarf itself, an Earth-like or larger planet is capable of blocking out increasingly more of the flux, giving rise to deeper depths, deeper transit depths. Now, if we consider CVs in which the white dwarf mass is fixed at a typical value of 0.8 solar, and this time we increase the donor mass, we find that the transit durations become increasingly longer. This is most noticeable for large Jupiter-like planets. One of the ideas that Roseanne and I brainstormed about in relation to this project was the possibility of advanced civilizations harnessing the energy of X-ray binaries in their stellar neighborhoods. I find it very intriguing to think that if ET were capturing the energy from an X-ray binary using some sort of Dyson structure, perhaps signatures of this structure could be detected as unusual features in the X-ray transit light curve. To conclude, we use the recent derivations of Gongji Li and her collaborators here at Harvard to estimate the transit probabilities around some example systems. This is a plot of probability versus mass ratio for 3 types of systems, including CVs in the solid line, neutron stars in the dashed line, and black hole binaries in the dotted line. And we find that the results are pretty encouraging, with probabilities in the few to tens of %. And so our next step is to put our idea to the test and examine archival data for signatures of transiting planets. Thanks for your attention, and I'll take any questions. We haven't done those types of calculations. The only survivability types of calculations we've done so far are for tidal disruption. But yes, that's a really important idea to consider.
Given the fact that the objects you're studying are the endpoint of an object that underwent significant mass loss, do you have an idea of how far out these planets might have been before these exotic objects formed, given the fact that the gas through which now these planets are orbiting will have brought their orbits in?
That's something that we haven't considered through modeling, but as I talked about in the introduction, if we look at the before and after cases, it appears that the planets are pretty close to the stability limit. And so perhaps whatever evolution happens prior to the XRB phase, it allows them to come back, perhaps come back to that stability limit.
And would could that explain the pileup that you referred to? That all these planets come in due to the mass loss of the progenitor stars, and those that venture beyond that boundary are unstable. And so it would naturally seem that they would continue to migrate in up to that boundary, and then you wouldn't see them anymore.
That sounds like a fascinating idea. I think people like Caitlin Crater are working on that, but that's something that was sort of beyond sort of the proof of concept that we were trying to demonstrate here.
Any other questions?
That was great. Thank you. Excuse me. Thank you.
All right, thank you.
Thanks. Oops. Can you pass this on?
I'm at UC Berkeley, and I'm just going to tell you about a project I've been working on with Lars Bilson and Bill Paxton at, you want to, yes. I'm going to totally screw this up. All right. So this is a project I've been working on. I should probably not try to do two things at once. With Lars Bilson and Bill Paxton at UC Santa Barbara on modeling the 3D effects of Rayleigh-Taylor instability in type 2p supernovae. And this over here is a movie of the Earth blowing up. And the reason I put that there is to remind you that I'm an numericist at heart and in practice. So if I say anything horribly wrong about type 2p supernovae, hopefully you'll call me out in a very embarrassing way. So first, let me explain the problem. You have type 2p supernovae, so the P stands for plateau. They're very common. This is a pretty typical one, light curve of a type 2p. You have about 100 days. P stands for plateau, so it's a plateau for about 100 days. And during that plateau phase, what you're just looking at is essentially the photosphere is moving through the hydrogen inward. And then you have this steep drop once it moves from the hydrogen into the helium, the other metals, and then becomes optically thin, and you're just looking at cobalt decay. And so these supernovae are very common, and we think we understand them. The progenitors are 8 to 10 solar mass single stars. Since they're single stars, we should be able, if we know anything about stellar evolution, we should be able to model these single stars very accurately. So it should be possible to have a complete end-to-end model of a core collapse supernova that can match these light curves. Unfortunately, there's one sort of missing link that makes it difficult to model these supernovae, and that is mixing. So if you don't do anything with, so if you just model, using a typical stellar evolution code like MESA in 1D, the abundances as a function of mass coordinate will just look like these step functions, right? So then when you carry out a supernova, if you carry out the supernova in 1D as well, this isn't going to mix the abundances around because you're just in 1D. And your light curves, what happens is once the hydrogen passes, once the photosphere moves past the hydrogen, you get a much sharper transition. In fact, you can even get these funny artifacts like this little ski ramp, which you never see in type 2P supernovae. So, but all you have to do, if you want it to make your light curve look nice, is you just mix these things up like this, and then you get a nice type 2P light curve. The only problem is, this is sort of the state of the art right now, is to just sort of perform the mixing by hand, and then try to sort of match it. So all of this interesting part, all where you're looking at everything other than the hydrogen, is sort of mixed out without any sort of first principles modeling. So so I wanted to sort of try to improve upon this a little bit. So what's causing the mixing? Well, the best candidate is Rayleigh-Taylor instability. So I have to quickly, in 1 minute, teach you all what Rayleigh-Taylor instability is. So in the lab, it looks like this. You have a high-density fluid balanced on top of a low-density fluid, and you have a gravitational field, and the high-density fluid wants to be on the bottom, low-density fluid wants to be on the top. So it's unstable. But you also get the same thing in lots of astrophysical contexts, but usually instead of a gravitational field, you can get the same instability in an accelerating reference frame, if Einstein is to be believed. But so in this case, if you have a high-density fluid decelerating as it collides with a low-density fluid, or a low-density fluid accelerating into a high-density fluid, you'll also get Rayleigh-Taylor instability. So for example, if you have some ejecta colliding with some circumstellar medium, the contact discontinuity between them is unstable. So I'll quickly show you a picture of an unrelated Rayleigh-Taylor calculation I did just because it looks so nice. But this was for relativistic Rayleigh-Taylor instability, so it's not applicable to type 2Ps. But I just like this slide because it looks very nice. But it gives you a picture of what this sort of instability looks like. In type 2Ps, the part that's unstable is actually as the shock is propagating through the star. So if I look at the velocity of the shock as a function of as it propagates through the star, it looks like this, and you get these spikes, and these spikes are at composition boundaries, so from oxygen to helium and helium to hydrogen. The reason is because you have these steep density cliffs in the structure of the star, and so as you go sort of down this steep density cliff, you get this acceleration as you go down this steep density gradient. And then once you hit here, you start decelerating as the high-density helium is colliding with the low-density hydrogen. And so that's when that configuration is Rayleigh-Taylor unstable. And so you could do the full calculation in 3D, but that's very expensive. And if you want to do a bunch of modeling of a whole bunch of different progenitors to sort of try to explore the parameter space of type 2P supernovae, it can be very difficult to do in huge 3D calculations. So instead, there's a sort of different idea which tries to sort of get sort of in between 1D and 3D, which is, it's not 2D, but the idea is to mimic the effects of mixing, of the 3D effects of mixing using a 1D model. So what I have here is, so the black is just the regular hydro equations in spherical symmetry, and then the red are sort of terms that I add in building this model. So and I basically just constructed the stupidest, simplest model I could. So I just added one extra quantity which represented the magnitude of turbulent fluctuations, and I have a source term which grows in regions which causes it to grow in regions that are unstable. I also have a decay term, and then this eta quantity is based on how large the turbulent fluctuations are. I have a diffusion coefficient, which sort of tries to mimic the mixing that happens in 3D. And so here's an example case of where I was sort of calibrating the model. So I would run sort of an idealized supernova calculation, a very, very idealized calculation in 1D and in 2D. And so, you smear out this sort of sharp density spike, which is totally artificial, and you sort of mix sort of this fluid with that fluid. So this is sort of the abundance. And the idea is to sort of calibrate this model so that I match the 2D case. And then, so when I first wrote down this model, it was just sort of for fun, because I wanted to see if I could do it. But then sort of Lars Bilston decided that this would be useful for type 2Ps. So he said, well, first thing you should do is actually calibrate your model to 3D, because otherwise no one will believe you. And so I did that. So this is the 3D version. It's still a 1D model, but it's now calibrated to sort of 3D results. So the idea is I write down this very simplified model, and I have a few sort of dimensionless coefficients, because I don't know what the true exact growth rate is, but I can estimate it and then put a dimensionless coefficient in front. And then I sort of tune those to match, so that the sort of 3D calculations match the 1D. And then after I've done that, we sort of we built a whole bunch of supernova models, progenitor models, and exploded them, and in both 3D and in 1D, and tried to see how closely we matched with a whole bunch of different progenitors and explosion energies. And so now it's up to you to decide whether or not this is like close enough agreement for your taste. But the nice thing is, I basically always get about this level of agreement, no matter how I change the progenitor. So the colors are the 3D, and the dashed curves are sort of the 1D model. And these are sort of abundances as a function of mass coordinate for different things. The other thing that's great about doing this is it not only mixes up the abundances, but you can also mix out, smear out these density spikes, which are artificial. So this is the case. Now, by the way, now that I'm going to assume that now this is enough to convince you that my model is perfect and beyond questioning. So from now on, we'll just work under that assumption. So. But the point is, in 1D you get this sharp density spike, and it gets completely smeared out in 3D. And when you do that, you're also sort of rearranging the velocities. So the velocity as a function of mass coordinate looks very different too. And then you might say, okay, well that's like 1,000 kilometers per second of difference. But what's important is that actually the rate, as the photosphere moves inward, the rate that the velocities change is significantly different. Okay, so I'm moving fast, so I'll be done pretty quick. But I just wanted this one last slide. This is very, very preliminary. Actually, I don't know if Lars knows I have this plot, but this is one quick one we've done with actually including using. This has been implemented in the MESA stellar evolution code in the hydro module, and we're doing. We're doing these type 2P supernovae. So this is an example when you turn on the Rayleigh-Taylor instability and you turn it off. So we can get rid of that this horrible artifact, and we don't have this sharp transition. Again, this is sort of the velocities as the photosphere moves inward, and you can see when you start to move into the helium and the other metals, you get a very different evolution for the velocities. When you include the Rayleigh-Taylor. All right, so that's all. Thank you very much. Yes. It is important for other types of supernovae, although I should say I'm not as good. I haven't worked on other types of supernovae, so I can't say my knowledge of them isn't as good. But the reason that we're focusing on type 2Ps right now is because they're so common and we think they're well understood, and so we should be able to sort of do the sort of best possible, most accurate modeling of these supernovae by including this mixing. But yeah, it's surely relevant in other supernovae.
You showed how someone in the past, I think it was around 2007, had introduced mixing, and I assume that was in a more ad hoc way.
Yeah.
I wonder if you can say a little bit about what they did, and does that have any connection at all to the result that you get when you try this type of process of making contact between the 1D and 3D calculations?
So I don't want to make any of these people mad, but basically what they did is really just pick some region and smooth over it. There's no sort of physical reasoning. It's just based on, I need the light curve to look like a type 2P. So that's probably the mean way to say it, but I'm sure they would have a better way of saying it. But this is, the thing is, this is sort of what you have to do if you want to do it. If you want to do a 1D calculation, this is sort of you're hamstrung unless you sort of do something to do this mixing.
Okay,
So
now let's take what they did, what they came up with, and
Yes.
it's a very ad hoc way,
Yes.
and what you came up with
Yes.
in a physically motivated way.
yes.
Does it agree? I mean, by getting the light curve to just look right, did they essentially come up with what you did by using the physical principle?
Yeah, I don't know the answer to that question, but I'm guessing that it might work for a particular supernova, but the amount that you're supposed to mix it is not, is not clear. Maybe, some will have more mixing than others, so,
It's always good to work from first principles.
yeah.
I would agree.
Yes, so I had a question about, so you said that you tune some of the parameters of your model to a 3D simulation. So
Yes.
I was wondering, is this, do you imagine like one set of general parameters that work for any kind of progenitor or any kind of situation, or do you have like different sets for different 3D simulations?
The idea was to do one set of parameters that's supposed to work for everything. This is sort of a new thing, so I'm open to the idea that there will be extra things you may want to include in your model. But at the moment, the idea is basically, there's only two times that I recalibrated. One when I calibrated it to 2D, another one when I calibrated to 3D, just because you're going to have slightly different, there's more modes that are growing in 3D, and the sort of decay rate is different. But yes, once I calibrated this to this one idealized model, then I just fixed all my coefficients. You're free to vary them in Mesa, but I don't recommend it.
Last question.
But it would seem like there's all kinds of applications. I mean, convection comes to mind. Do you think you can do convection this way?
So that might be trickier, but I'm definitely open to it. I mean, there's no reason that you should be able to do this, actually. So I just sort of wanted to see if I could. And it turns out that it's possible. That, you can't really tell until you try. So it may be the case that that's possible. Sorry.
Okay, can everyone hear me? Okay, nice to see you all again. My name is Graur, and I'm going to describe a paper that we recently submitted some 2 months ago to AppJ about tidal disruption events. I usually talk to you about supernovae, but I figured I'd do something different for a change. This is work I've done with a few collaborators. I wanted to give a shout out to Jabran, James, and Casey, who are all postdocs here at the CFA. Without their help on this paper, it would have been much shorter and far less interesting. So, tidal disruption events happen when an unlucky star happens to stray within the tidal disruption radius of the supermassive black hole in the galaxy, or any galaxy. If the supermassive black hole has a mass so that the tidal radius is outside of the Schwarzschild radius. And if the star has a mass and radius with some relationship to the black hole's mass, then that star will be torn apart by the gravitational force of the black hole. Roughly half of the star's gas will be unbound and thrown out into the ISM, while the other half will fall back onto the black hole. We think that when it does that, it should form an accretion disk. And during the formation of this disk, there should be a very bright flare that should peak in the UV and X-rays, and that should be visible out to great distances. This last flare is what we call either a tidal disruption event or a tidal disruption flare. You'll see both acronyms used in the literature. Now, TDE candidates started popping up in the 90s, just a couple of years after the first theoretical paper about this. These were usually based on archival data with not too many points on the light curve, so it was hard to claim a very firm detection. In the 2000s, when the large transient surveys came online, surveys such as the Palomar Transient Factory, Pan-STARRS, and others, people started discovering these in the optical and did multi-wavelength follow-up immediately. So you started getting much nicer light curve with coverage in different wavelengths. And so what has been found so far is around 70 candidates. Some of them show the expected decay as t to the minus 5/3 expected from theory. Some of them also show broad hydrogen or helium lines, or sometimes a combination of both, in their optical spectra. So there are now around 70 of these candidates. You can see all of them on James Gillishan's open TDE catalog on the internet. It's not clear how many of these really are TDEs or AGNs behaving badly or some other type of transient phenomenon occurring in the center of the observed galaxies. It's not even clear that the objects we call TDEs and will fight people to death over calling them TDEs really are what was expected from theory. This is a brand new, very emergent field. So we're still at the stage where we're collecting different butterflies and trying to understand whether everything we have is just a butterfly or maybe moths exist as well. So Katie Oshetel, who is a postdoc at Ohio State, took all of the TDE candidates on the open catalog and examined all of the available X-ray and optical data. And she classified these into several categories based mostly on their X-ray data. So we now have I would say, a first stab at trying to understand which of these candidates should be thought of a little more seriously and which should be placed aside. Now, I come from supernovae. This is the first time I've looked at TDEs, but I've been looking at supernovae and their host galaxies. So the first thing I wanted to do was just take all of these and analyze their host galaxies spectroscopically and photometrically. Now, I'm a lazy astronomer in that I prefer using other people's data. It's so much faster and easier. And so what we did was analyze 35 out of these 70 host galaxies for which there was already public spectroscopy. And what we wanted to do is test the very basic idea of a TDE. So I said that the idea is that this is a star disrupted by a black hole. And it's a very nice story. Theorists tell very nice stories, but it's still a story. As an observer, you want to take any theoretical notion with as big a bag of salt as you can find. So how can we test this? If this is a star disrupted by a black hole, then the rate at which you get tidal disruption events should depend on the properties of the stars in the vicinity of the black hole. A star will be disrupted if it's flung into the loss cone of the black hole, this geometric area in space within which the black hole will disrupt the star. So this should depend on the density of the stars. The more stars you have, the higher your rate will be. And it should depend on the velocity dispersions of the stars. The lower the velocity dispersions, the easier it will be to fling one of these stars into the loss cone. Now, unfortunately, these properties are on sub-parsec scales. So good luck trying to measure that. We can do this within our own Milky Way galaxy, but it's taken people decades of very painstaking adaptive optics observations to track stars around Sagittarius A star. I'm a postdoc. I don't have a decade. So instead of looking at sub-parsec scales, we wanted to see whether instead we could look at global galaxy properties on kiloparsec scales. And so out of the 35 galaxies we analyzed, 10 had density and velocity dispersion measured in exactly the same way as a background control population of SDSS galaxies. So we can do an apples-to-apples comparison between our host galaxies in purple and the background control sample. And we find that TDE host galaxies significantly prefer denser hosts. There's also a gray population here. This is a second population of host galaxies that have these properties measured in a similar way to the SDSS, not exactly the same way. So they're not used in any statistical tests, but it's still encouraging to see that they all fall within the same space. If we divide the galaxy sample into star-forming galaxies in blue and passive galaxies in red, we find that the reason TDE hosts prefer passive galaxies is because most of them are in passive galaxies to begin with, and these galaxies are already denser than the rest of the galaxy population. TDEs in star-forming hosts are in galaxies that are denser than the rest of the star-forming population. So based on this, we built a model that simply assumes that the rate is proportional to power laws of the density and velocity dispersion. And we fit for the indices of these power laws. And once you fold in the known M-sigma relation for black holes, we found that our results were consistent with exactly what you would expect from dynamical relaxation of stars around the supermassive black hole. So points for the theory. We did another test. As I said, this is a very new field. And a couple of years ago, Yair Arkavi looked at a sample of 8 of these TDEs and found that most of them were in post-starburst or E+A galaxies. These are galaxies that have very little age alpha emission, but quite deep age delta absorption, which tells you that these are passive galaxies that had a recent starburst episode. These galaxies are extremely rare. They account for less than 1% of all galaxies. And so it was very weird to find these TDEs all in this region. And based on this, people internalized the idea that TDEs prefer post-starburst galaxies. Once you look at a larger sample, you see that this is not the case. TDEs are found in all galaxy types. not just post-starbursts. However, post-starbursts are still overrepresented relative to the small fraction of the general population. And this holds no matter what type of tidal disruption event you look at, whether it has X-ray emission, whether it doesn't, whether it has broad hydrogen or helium features or it doesn't, and so on. So in conclusion, what I want to show you is that we can use global galaxy properties on kiloparsec scales to test and measure the rates of tidal disruption events. We're no longer bound to local sub-parsec scales. We find that the host galaxies of TDEs are significantly denser than the background galaxy population, and that this is consistent with what you would expect from dynamical relaxation of stars around the supermassive black hole. We also find that post-starburst galaxies are not the majority of tidal disruption events. They are, however, still overrepresented. This might be because these galaxies are also denser than most other galaxies. But it's still a little too early to say that from a statistical point of view. So, thank you. So we haven't looked at that. There's another group that looked at other properties, but they didn't look at triaxiality either.
So the context where triaxiality is important is theory predicts that merging black holes have a much higher rate by a factor of 1,000 or more than the tidal disruption event rate in normal quiescent galaxies. So that would be tested if you look for merging galaxies.
So merged galaxies would also be much denser than background galaxies. That is a good point. That is something that people are looking at. You need usually HST observations to do that kind of work. So that's something for the future.
So are there any TDEs and ellipticals out of those 70? What fraction? And if so, are they ellipticals with central cusps?
So most of the TDE hosts in our sample are in quiescent galaxies. Most of which, if not all of them, will be elliptical. We didn't look at cuspiness and other such properties. We specifically wanted to test velocity, dispersion, and density. It is known that post-starburst galaxies tend to be more concentrated, even relative to other galaxies with the same mass and density. Again, that's something that you need HST for. There was one paper by Sjoerd van Velzen and Nick Stone from Columbia who looked at one such galaxy, and they make exactly that claim. But even with HST, it's hard because they have to extrapolate into the very inner regions of the galaxy. So that's tough.
That's the question, John.
Are there any TDE candidates that are not in the centers of galaxies?
No. So that's one of the ways you classify something as a TDE candidate is it at the center of a galaxy? Otherwise, it's some other exotic transient, and you write a Nature paper about it.
There could be a big black hole orbiting around the galaxy, not in the center. We have a easier talk about this in terms of TDE.
So John is asking if you can correlate it with AGN activity that may have been there to start with before the TDE.
No, my understanding, even if you have two merging galaxies, you can have an off-axis AGN. So you can get tidal disruption events, not specifically at the very center of the galaxy. That's true. That's not how observers are currently trying to classify these things. Even with the optical surveys, PanSTARRS and PTF, many of these objects weren't discovered in real time so much as in archival searches. Once people became aware of tidal disruption events, they went back and searched the data and just said, show me everything that's in the center of a galaxy and has these many points and decays in this way. And I'll call this a TDE candidate. So what you say is very true. It depends on whether the people within the survey have what you say in mind or not. So far, the answer has been no. But that's something to remember for the next ones.
Thank you very much.
Thank you. Hello. Well, this will be a little comic relief after the other talks. People I've met with yesterday and today have all been curious about what the writing life is like, so I thought I would talk a little bit about that. And my writing life was heavily influenced by Carl Sagan. I went to a public lecture that he gave in the early 1970s, and it's not an exaggeration to say it was a life-changing experience. And I got to write about him quite a bit when I worked at Cornell as a science writer in their news bureau. And then years later, when he was working on the Cosmos series, he wanted somebody attached to the production team who could answer questions from the public, if any such arose. And I got that position, so I traveled with the production team in Italy and Greece. And for most of the time, I wondered what I was doing, because there weren't that many people around asking questions. But one morning in Greece, I arrived on the set. There was a scene being filmed at an amphitheater with a fire at the center, and then on each of the tiers, there was the flag of a planet. And they had put Saturn before Jupiter. And I thought, at last, I can make a contribution here. And it was a good thing, because that really would have made him very upset and ruined everybody's day. And then a few days after that, the script girl, who was really about the busiest person, fell and hurt her ankle. And I'd just been watching her work for a couple of weeks. So it was easy for me to step in and do that job. And then I really was making a contribution. I worked for a few years on the Science Times, the Tuesday section of the New York Times, when it first began. And and I couldn't write about astronomy at all because Walter Sullivan and John Noble Wilford were still on the staff. So they assigned me to psychology and psychiatry, about which I knew almost nothing. So it was terribly stressful on the job learning. And one of the things they did was volunteer me for a stint as a human subject in a research project about circadian rhythm, which just won the Nobel Prize in physiology this week. So the idea was to live in this artificial laboratory setting for a month and see what would happen to my circadian rhythm if I never knew what time it really was in the outside world. Glad I did it once, but I wouldn't do it again. one of the strange duties as a Times reporter is to write the obituaries for the people on your beat. And when Erich Fromm died, I was off interviewing somebody and got called back to the office and had to put together his obituary in a big hurry. And that was awful, and I didn't ever want to be stuck doing something like that again. And so I looked at who on my beat had a prepared obituary. That's how it's usually done, long in advance. And I noticed that B.F. Skinner had no prepared obituary, so I thought I had better tend to that. And there was a fellow at the Times, his name was Alden Whitman. They called him Obitman Whitman. And he was the one who created the wonderful practice of the very lengthy, detailed obituaries. And so he told me what to do. He said, you write him a letter and tell him you want to prepare a detailed biographical sketch for future use. And he'll know what you mean. And tell him that you would like 6 hours of interview time, preferably at home. And, oh, make sure you read everything he's written before you go up there. So I did the reading, and I wrote him the letter, and he was sorry that he could not spare 6 hours. He could give me 2 hours. And being a behaviorist, he had a way of meeting with reporters, and that was to meet in his office. So I was very nervous going into this. You know, felt like the Grim Reaper. And as soon as I got there, he said, have you come to write my obituary? And I said, yes. And he said, oh, good. You know, I'm so relieved because one worries about these things. So we had a great time. Every time a student came in, he would say, this is Miss Sobel from the Times. She's here to write my obituary. And the student would just blanch and gulp. And so then I wrote it. I mean, it's that first sentence that you really have to think about, how you encapsulate the person's lifetime achievement. And after I wrote it, I sent it to him. And he made some very helpful suggestions. And then I'm happy to report he lived for another 8 years because I was very worried that somehow, you know, by doing this, I would jinx him. It's not scientific, I know, but that was my fear. So when the obituary appeared, I had already left the Times, but it was B.F. Skinner. It was still a page one story. And they gave me a byline. And I heard from a number of his colleagues who said things like, that was the first time I ever saw the concept of negative reinforcement correctly explained in the popular press. Fred would have been pleased. And I thought, well, he was pleased, you know, because he read the piece and corrected it that I got everything right, which is really the way to go about writing about science, I think. So one of the stranger assignments I got in my freelance life was to cover what never happened in Roswell in the summer of 1947. And I went to the town. And has anyone been to Roswell? Okay, well, there were 2 museums devoted to the landing. And of course, there's nothing in either museum. It's really remarkable. And, you know, they have a diorama of the crash site, and they have department store mannequins in operating room scrubs performing alien autopsies. It's really very silly. But they also have Robert Goddard's workshop, because that's where he moved once he was successful setting off rockets. He couldn't really stay in Massachusetts. But this enterprising fellow was advertising that he owned the crash site. And if you signed a permission form that said you understood all the dangers of going to the crash site. He would drive you out there in his pickup truck. And the dangers had nothing to do with being abducted by aliens. It was all things like snake bite and scorpion bite, and nothing happened. You won't be surprised to hear that nothing happened. And this is one of the strangest, most moving experiences of my life that had to do with writing Galileo's Daughter, and realizing early on that the story really hinged a lot on understanding the Catholic religion. And although I could speak Italian, I had many necessary prerequisites for writing that book. I was raised Jewish in the Bronx, and the Catholic faith was much more complicated to me than anything in Galileo's science. And I looked for a modern-day convent of the order to which his daughters had belonged, and I found one in Roswell, New Mexico. And there was the headquarters, and the federal abbess of Poor Clares in America was in Roswell. And so I started a correspondence with them, which was extremely helpful. There were many questions that I couldn't find answers to. Is that my time up? And so she, questions like, why is Claire the patron saint of television? Somebody who lived and died in the 1200s. A lot of things are just hard to understand. But she answered all my questions, and they prayed for me, and they read the manuscript. I mean, these are people, they spend maybe 20 minutes a day reading, and they're silent all the time. But during their meals, they're read aloud to. And so she read aloud the manuscript, and she made suggestions. And at one point, she said that some of the sisters wanted to do higher studies. And knowing that they lived completely on charity, I thought this was my chance to give something back. And I offered to be their Book of the Month Club. And at the beginning, they would tell me what books they wanted, and I would order them. And they would be from places like the Paulines or the Franciscan Messenger Press. And then, I don't remember what happened, but I was traveling a lot, and I couldn't keep up with them. So I said, here's my credit card number. Just take it over. And she wrote back to me, we resisted the temptation to buy a villa in France. And this has continued. Now, remember, they were all religious books. I knew Cardinal Ratzinger long before he became Pope, because he was the regular author of the books they requested. But last spring, was it just last spring? Maybe a year ago in the spring, they always tell me what books they buy. Well, they saw a really good sale happening on the Great Courses website. And what did they buy? Understanding Our Solar System, something about the Hubble telescope, and one on crafting better sentences. And I just, we've touched each other over the years. And there is now, the original abbess has died, but we now have the Mother Mary Frances Memorial Library. And it's big, I'm happy to say. So that was a wonderful time for me to really expand my horizons. Do you have any questions? You could have your obituary all ready to roll. It's a good idea.
Were you at the Times long enough to have contributed to Carl's obituary?
No. No. No, he died in, was it 1996? Yeah, no, I was long gone. All right, thank you. Okay.
My name's David. David, yeah. Actually, a couple of years ago, while I was an undergrad working with Yair Harvey on some of his tidal disruption event work, I'm just curious if you've seen any of your new discoveries about the TDE population being incorporated in surveys, like searches for TDEs.
So Yair himself had a survey looking for TDEs specifically for Star Wars Galaxy.
I helped write the code for that survey.
Okay.
Yeah.
As far as I know, nothing has come out of it.
Okay. Yeah, I left before they started really getting results, so I don't know quite what's going on with it.
Okay, and I haven't heard anything.
Yeah, it's so great to be able to tell
But
stories
I
like that.
don't
It's
expect them to find
Really?
that much, no, because they're not the majority. So I think it would make more sense to target just
dense galaxies.
This is not from the box.
Seen anyone making moves towards targeting dense galaxies?
No, not yet. The thing with targeted surveys, it's harder to get targeted surveys going, especially when the TDE itself is low. It's lower than the Supernovae. So take that and add to that the fact that most of the surveys that move to untargeted surveys where you can just look at the big patch of the sky and just find stuff in all types of galaxies. It's more agnostic in a way, and it requires